introduction because you need a chairman. You can never stop.
Would you like to say anything?
It's a great pleasure to have the opportunity to speak on this occasion. Let me begin with a question. Who is the coolest in the gang? We all know the answer, it's Prakash. So, notice the uncanny, we're both on rooftops. This one is on the top of a tower in Lyon with Prakash, Peter and myself. I lost my glasses somewhere on the way, I haven't managed to find them. I remember this was quite a tower, quite a steep hill. You remember Prakash complaining vociferously about the steep hill all the way climbing up. And I said,
I was just worried whether he would make it.
I see. Well, I said, what about all this tennis you're playing? And you said, I haven't been able to keep on my usual fitness regime because the gym burned down. That's the excuse I've ever heard.
Absolutely true though.
So, Prakash and I have known each other for many years, and in all that time I've obviously admired his way of doing science, his way of engaging with people and of having fun, managing to do all these things together at the same time in an entirely natural, graceful, apparently effortless way. So I continue to admire that very much. So there's lots more I could say, but I'd like to use my time to talk a bit about science, particularly as the topic of the talk concerns two of the major themes of Prakash's work, namely probability and physics, more particularly quantum information. So let's start with a little kind of toy situation. We have a system with two bit registers. The rules of the game are each time we can read one of the registers but not both, or we can ask for the exclusive OR of those registers. So either read A, read B, or read exclusive OR of A and B. And we do this repeatedly, and what we observe is that when we read A, we always get the value 1. When we read B, we always get the value 1. When we read the exclusive OR of A and B, we always get 1. How can this happen? We could try and explain this behavior by some kind of mechanism, that there's some unseen power setting the values of these two registers, and maybe it chooses the values that it sets from some probability distribution. Okay, so it throws a dice and decides which of the 4 possible joint settings to make in the registers. And it's quite easy to see that there's no such distribution which we can find which can yield the observed behavior of this system. You like to think about that, but you'll easily convince yourself that that's true. But consider the following strange thing we could imagine. A signed distribution. Notice it still normalizes to 1. And now if you look at these are not directly observable things. They are secretly the settings of the two variables. And now if we look at the observable events, and we look at their probabilities, we see that they yield well-defined probability distributions. So the probability of A being 1 is 1, but the probability of A being 0 is indeed 0. And of course, because we get some cancellation with this negative sign, and similarly for the other events. So somehow, by introducing a negative probability, we make apparently impossible behavior possible. Well, this sort of general picture of things that we can look at directly and trying to explain them by some kind of mechanism sitting behind is really a version of the whole story of hidden variables, or what Mermin nicely describes as instruction sets. So here are Alice and Bob, who can choose different variables to look at, and they can see the outcomes of their observations of these variables. And we can imagine this being done repeatedly and seeing some statistics for these things. And we can try and explain what they see in terms of a source that's setting the values of all these variables and maybe sampling them from some probability distribution. So here is a famous example that's loomed quite large in recent work in quantum information, the Popescu-Rawling box. So here's Alice Alice and Bob. Alice can choose either to look at variable A or A prime. Bob can choose to look at B or B prime. And we see that we get very highly correlated behavior in this, according to this statistics. If any of the variables other than A prime and B prime are chosen, we get highly correlated behavior, both 0 or both 1. Whereas in the case of A prime and B prime, we get anti-correlated behavior. The variables must have opposite values. And this is an example of something that exhibits correlations, non-local correlations that are so strong, not only do they exceed possible classical explanation, but they also exceed what we can do using quantum resources. So using the Tirelson bound, it follows that no way of representing this with an entangled quantum state and so forth can give this kind of behavior. So the instruction set is just now setting values for all of these variables together. And once again, if we introduce these weird notions of a signed measure, the situation changes. So here's a particular signed measure that we could introduce, and we can check that this distribution reproduces exactly the probabilities of the PR box. For example, let's take this case. If we choose the variables A and B to measure, then the PR box tells us that we get a 0 probability of seeing the outcome 0, 1, the anti-correlated behavior. That's one of the entries you see in this table. And indeed, if you think about what this event is, the way this event, so to say that A gets outcome 0 and B gets outcome 1 is to say the first of this string is 0, it's A, A prime, B, B prime, and the third is 1. And there are 4 of these strings which match this condition. And you see if we sum over all of these, again we get a cancellation here because of this negative, and we get probability 0. And every entry in the table comes out exactly right using this sign distribution. And this isn't an isolated example. In fact, there's a general result from a paper from a couple of years back with Adam Brandenburger, which says that for really quite a general class of such probability tables, which includes all the Bell kind of scenarios with any number of parties, measurements, outcomes, but also things that go quite a way beyond tension-Specker configurations and lots more things, the following are equivalent. The model can be realized by a signed measure on instruction sets, and on the other hand, the model is no signaling, which is an important condition motivated by physics. So what is this no signaling condition? It says that when Alice and Bob perform measurements in space-like separated locations, the marginal probabilities for Alice's observations of outcomes for the measurements are independent in the probabilistic sense of Bob's choice of measurement setting. So there isn't enough time for Bob's choice of measurement setting to have an influence on the statistics that Alice is going to see for her measurement outcomes. This is taken to be a basic condition to ensure compatibility with relativistic constraints. And by the way, this Popescu-Rorlich box satisfies this condition. So we understand that it's consistent with relativity. On the other hand, it does more than quantum mechanics allows us to do. We don't really understand what principle separates those things. In fact, a lot of the current research in quantum information and foundations is trying to understand exactly that point. So we have the classically producible correlated behaviors. This, so I've shown it with sharp edges here because it's a polytope. If you think of all the probability vectors we could get of that form, it's defined by inequalities. There's a much bigger polytope of all the things that are consistent with no signaling. And sitting in a subtle way between these two is the quantum set, which is not a polytope, is a convex set. I'm trying to understand why nature selects this green area out of this larger blue area is what a lot of current work is motivated by. So, in a sense, if only we were sort of, so in a sense this is giving a characterization of the no signaling behaviors. It's saying that we can't use negative probabilities, which by the way have been discussed by Feynman, Dirac, Wigner, Weyl, and various other eminent people, but we can't use them to explain quantum phenomena just by themselves, because actually they give us this whole class of no signaling behaviors. But if we want to think we're explaining anything with negative probabilities, first we have to explain negative probabilities. And what I'm going to describe now is a kind of operational interpretation of negative probabilities. And as we've just seen, if you have an operational scheme for producing such things, then in a sense you can use this to realize, to simulate arbitrary no signaling devices. So the idea is that we to postulate a kind of mechanism to reduce these negative probabilities to things that we can understand in a more concrete way, to standard probabilities. The idea is, so to speak, to push the minus signs inwards. So we think of signed events. So the idea is that we're going to have positive and negative, some primitive piece of information that tells us for each occurrence of an event whether it's occurring with positive or negative signs. And the idea is that positive and negative things cancel off. Which gives us, if we're taking some frequentist account of probability, the idea, instead of the usual relative frequency, of a signed relative frequency. So if you have a bunch of these signed events, the relative frequency you're interested in is the difference of the positive occurrences of the event and the negative occurrences, where the total weight of the ensemble is itself measured by taking the total weight of the positively occurring events minus the negatively occurring events. So this arithmetically reflects this idea that positive and negative occurrences of the same event. So how do we write this a little more formally? Given a set, we sort of have the usual idea of the discrete probability distributions on the set. We're also going to take the set of signed measures, where we still keep this normalization condition does play a role in our considerations. And as is familiar, these things are functorial. We can push, given a map from one set to another, we can push either signed measures or probability measures forward along the map from being measures on X to giving us a measure on Y by a formula that I guess is familiar, and this is factorial. So how do we represent signed measures? How do we formalize the picture that we were just describing? So given a set, we just take two copies of it. So we could say the disjoint union of two copies of X, so we use the notation for the two copies of X plus and X minus. Laziness, here we are. Okay, so it's really just X plus X, but this is just a notation for it. Then the representation of a signed measure by a probability measure, a signed measure by a standard probability measure on a signed version of the set is just formalized by this map here, which does the obvious thing. It takes events of positive measure and puts their weight on the positive occurrence of the event, and it takes those with negative measure and puts them on the negative occurrence of the event, but now with the absolute value, so it's a positive value, and we normalize by the total weight here. That gives us a standard probability distribution. And there's also a map that comes back, which formalizes this idea of cancellation. So given a standard probability distribution on this signed version of X, two copies of X, we can come back to a signed measure on X simply by cancelling off the weights on the positive and negative occurrences of each event, normalized by the total positive weight, the difference between the total positive weight and the total negative weight. Of course, we need some condition to be sure that we're not dividing by zero, but that falls out naturally. You may notice that we'll always have this thing, we'll always have the total positive weight being greater than the total negative weight from anything that comes from a signed measure. So we can build that condition here. And then the sort of little property that says that things work sufficiently well functorially, which we'll use in looking at our simulation result, is this one. Just the fact that this diagram commutes. That the simulation works sufficiently well with respect to pushing maps forward, in that the effect of pushing a map on a signed forward on signed measures is the same as representing the signed measure by a standard probability distribution on the signed events, pushing the map forward down there, and then coming back in the way that we just showed here. The two things match up. Okay, let's come back to the instruction set picture. And we see that we can make almost exactly the same picture as the standard Mermin picture that we saw earlier. The difference is now that we have this extra bit of information on each event that's being generated by the source. Remember, the source is globally writing values into all the variables. If we want to think, and then Alice and Bob inspect, choose particular variables to look at on each round and record their joint outcomes. And we think of this arriving at some target over here. And instead of just having those events as the ones on which we sample from some probability distribution, we're now imagining they come with this extra bit of information, which is this sign, positive or negative. And that information has to be propagated through to the target. It's not used by Alice and Bob. They do exactly what they did before. So what we're saying is we're given so in the situation we're considering, we're given a no signaling empirical model. So this is a standard probability model, something like the Popescu-Rawling box, with its conditional probabilities as tabulated in the table that we saw earlier. By the theorem we cited earlier, we can find a signed measure on the instruction sets which yields these observed probabilities by marginalization. So just by looking at all the instruction sets, just as we saw in the examples we looked at before, all the settings for the whole set of variables which restrict to give us the observed outcomes, then we recover the probabilities for those events that we see occurring. Now, given this sign measure, in order to actually give an operational account of it, we form this probability distribution, which is a standard probability distribution but now on signed instruction sets. The source produces this stream of signed instruction sets by repeatedly sampling from this concrete probability distribution, just a standard probability distribution with positive numbers. And the way we think about this thing physically in general, the way we think about these kind of instruction set pictures, is that the source is generating a stream of particles which come inscribed with their instruction sets. This will be the usual hidden variable picture. So those instruction sets tell the particles, when Alice chooses to measure her particle, Bob chooses to measure his particle, which answer to give for whichever measurement they may happen to select. And that's how we see the outcome. So exactly the same thing happens here. And it's important that Alice and Bob act independently of the source, I should say here. That independence is an important constraint. So they can choose whichever measurements they like, and this is not determined by what the source is doing, otherwise the whole thing will trivialize. The target receives, so therefore this is going to work despite the fact that Alice and Bob act independently of the source. And then the target receives its stream of outcomes and measurement choices from Alice and Bob as before. So if we were giving a frequentist account of the usual hidden variables picture, the target is actually looking at the incoming stream of joint outcomes, so it's seeing the usual relative frequencies as it gets a large number of these, and then the limit of the relevant frequencies recovers the predicted probabilities. In our case, it's again almost identical, but now the signs, this extra bit of information we got on each of those basic events, are used to compute a signed relative frequency rather than the usual standard relative frequency. And the idea is that the limiting values of these signed relative frequencies gives us back the probabilities. So let's just see that if we formalize this in standard probability theory, it works. So here's a little standard notation for indicator functions. So we're just going to think of random variables in order to fit in with standard probabilistic notions here. Of course, we recover the probability of an event as the expected value of the corresponding indicator function. Just the characteristic function of a set of events. And just as we did earlier, we're going to be interested in looking at some particular event where we're looking, say, at Alice measuring X, Bob measuring Y, Alice seeing result U, Bob seeing result V. We're going to be interested in the set of instruction sets, the set of assignments to the whole set of variables, which give us back those results for that choice of variables. So the consistent events of assigning to all variables that give us back the actually observed outcomes for those particular variables. We're going to have signed versions of these sets. So once we do that, we can then write down some independent, identically distributed sequences of random variables, which would be a standard way of formalizing the way that we get these streams of events that we've been describing. So here is an IID sequence for the positive occurrences that we're going to see according to our distribution that we've got down here in our scheme. The one that we produced by the theorem, and then translated into a standard probability distribution on signed instruction sets. And then we're going to look at the positive occurrences for the things that will give us outcomes U and V for choices of variables X and Y. And similarly, one for the negative occurrences, and then something corresponding to the total mass for the positive occurrences of instruction sets and the total mass for the negative occurrences of instruction sets. Now this looks like a description of the whole stream of things we'll have, regardless of the choices that Alice and Bob make for which variables to look at. But it turns out that this equally well applies for the subsequence that we would pick out by conditioning on a particular choice of variables that Alice and Bob choose to measure. This follows just from the trivial point that infinite subsequences of IID sequences are the same as the original infinite sequence, but also uses the fact that, as we were saying, the measurement choices are considered to be independent in the probabilistic sense from the distribution that we're taking of the source. That's a fundamental assumption that is needed for all the usual results in the foundations of quantum mechanics. So continuing with this, then, the process of forming signed relative frequencies just becomes forming this sequence of random variables, which is exactly the difference of the positive and negative occurrences of the relative of the appropriate kind of events that will produce the behavior so we're looking at a particular case. Alice having chosen X and seeing outcome U, Bob having chosen Y, variable Y, and seeing outcome V. So this is the total number of occurrences in the stream of what we see of those events in the signed sense of the difference between the positive and negative occurrences. And this is the total weight of the whole stream of events that we're seeing, the total sum of positive ones minus the total sum of negative ones. And the correctness of the scheme, the fact that we really get back the probabilities that we want, is just the fact that the limit of this sequence is equal everywhere except on a set of measure 0 to the probability that we're aiming to simulate. So this, of course, uses the standard strong law of large numbers. And the beauty of the standard strong law of large numbers, the strong version, is that convergence works pointwise on the sequence space, all the choices that we're making, outside a set of measure 0. And what that lets us do is break this limit up. So the usual strong law of large numbers takes averages of a single IID sequence of random variables. What this does is to break each of these up, take the average value, divide each of these by n, and apply the standard strong law of large numbers. Now, that's going to be valid in each case outside a set of measure 0. If we then take the union of those 4 sets of measure 0, we'll still have a set of measure 0, and everywhere outside there we'll get pointwise convergence on the sequence space to the values that we want for those things. and then just using pointwise properties of limits, we recover this result. So in effect, we get a signed version of the strong law of large numbers, because the details are in the paper. Okay, so I should be finishing up. Of course, I would describe this as a simulation, not a real physical process. As far as we know, there's nothing beyond quantum behavior. But it's a positive way of describing these curious things like PR boxes and other such no-signaling devices. It's certainly a different way of describing them, and because it's a different way of describing them, it may offer a different way of addressing the problem that we were mentioning earlier, namely homing down from the whole big no-signaling set down to the quantum set, the structural features that we can find that give us a way of picking out the quantum set. There are some questions that kind of a bit tantalizing here. This idea of cancellation of positive and negative occurrences. So, is there some hint of retrocausality in this idea of signed relative frequencies? In other words, to know whether an event counts, as it were, we need to know whether it's going to be cancelled off later on by some negative event. We may need to have some kind of bound on the rate of convergence to make this effective. So if you haven't been cancelled off by a certain amount of time, then you know that it's going to be included, so to speak, in the result. There are various other properties we could look at, additional properties we would look at, which would filter out from this larger class of no-signaling models down to the right ones. Okay, so I'll finish up here, and as you see, Prakash is still the coolest in the gang. It's a different book, yes.
So I guess a natural question to ask is how it connects up with Raphael's hierarchy of quantum measure theories. So he formulated this notion of a quantum measure,
Yes.
where you have no three-way interference, but you have two-way interference. And I was wondering if your assigned probability corresponds to the next level beyond that.
Well, that's a good question. I'm very interested in the quantum measure theory from a slightly different point of view, in that I think it could be used to, we have a sort of uniform picture that by taking probability measures on instruction sets, we get the yellow region. By taking sign measures, we get the whole of this. The thought is, by taking quantum measures, can we get the region we really want? The Goldilocks sort of thing. So the problem is finding a notion of quantum measures with good enough properties defined independently to really capture this quantum set. And that actually seems a bit elusive. It seems that there is a sense in which you can, certainly if you have a quantum realization, it induces a measure on the instruction sets, which does give you back the observed probabilities. And I was mentioning in the sort of lecture the other day in the spring school, one can actually leverage that to get some traction on some of the decision problems that arise in this region. But getting a nice standalone characterization seems harder.
Yeah. Well, that thing has a complicated shape.
It's very complicated. I mean, even these polytopes, although they're polytopes, are pretty complicated in various ways, but the quantum set has an extremely complicated shape.
One more short question. Yeah, it's two of them.
So a couple of days ago, when John Barrett finished up with his lectures at the spring school, he was mentioning some ways that one might possibly get around the no-go results. And one possibility you mentioned is that perhaps the framework of hidden variables that's used to prove all of these results isn't the only framework in which one could.
And one can only say that's fine, but would suggest an alternative?
Well, yeah, I'm asking, do you think
Yes.
this could be one? Because you're tinkering with something extra here. So do you think
Yes.
this might be such a...
Well, I mean, it's intriguing to think of, the thing here is that, I certainly wouldn't call this a physical mechanism, hesitate to do so. I mean, but in principle, all the ingredients are classical. You know, you have your billiard balls that just have a plus or a minus on them, as it were, and they go flying off, and then you compute these signed relative frequencies. So I hesitate to say it's a physical mechanism. On the other hand, physicists do postulate some strange mechanisms. But I mean, the one answer that occurred to me with one response that occurred to me to John's point was, well, you know, quantum mechanics itself is an alternative. But, you know, but yeah, I mean, I agree. Yes, it's always good to sort of try and think more widely about possibilities.
Okay, we thank Samson again.